Very good.
Okay, well, this is really exciting. We've been going to Telluride now for, how many years is it? 20,
27.
27 years. There's something magical about Telluride. And my goal here is to try to give you a sense, because a lot of people who are listening have never been there. And so we have traditions, we have, there's a tremendous amount of energy. And of course, all things neuromorphic go back to Carver Mead. And I sort of mark 1989 as being the moment when the world suddenly became aware of it, when Carver published his book, Analog VLSI Neural Systems. And of course, he had a group that had been developing this for quite some time. You'll be hearing a little more about. I was very fortunate because I did a sabbatical at Caltech in 1990. And one of the high points for that year was to attend the lab meetings at Carverland. So I actually got a chance to see, like, a fly on the wall, how this field developed from scratch. And it was really an extraordinary opportunity just to get to know everybody and see how it's all developed. So here's the, what it must have looked like. You can recognize some of the people. Shishi hasn't changed at all. She's right there on the left side. And here is a group photo. You will recognize several people. In addition to Carver, this is Kwabena Boahen, formerly known as Buster. This is Andreas Andreo, and many others that were there from the very beginning. Now, there's one other person that was mentioned briefly, but she played a very important role, Misha Mahawald. She was the one who was responsible for the first silicon retina, which really impressed me and many others. But she also had several other groundbreaking chips. One in particular that combined input as a stereo chip, but it was a collective chip in which you had interactions occurring, feedback interactions, which really was also very pioneering. And you also have to know that, she really combined her, one of the few people at that time. She was an undergraduate major in biology, and then, of course, went to Carver's lab, got her PhD there in engineering. So she had this dual brain that could combine the two disciplines. And they're very different, by the way. I mean, the way you think as a biologist is very different from that of an engineer or physicist. There was a paper that appeared in Nature in 1991, which was got a lot of attention and had a lot of impact. It was Misha and Rodney showing that you could indeed mimic Hodgkin-Huxley kinetics with a chip, and therefore actually create real silicon neurons. And this was a turning point because of the fact that Misha, she graduated shortly after that, I think it was 1991 or 2. She had the best thesis award, and a lot of people were graduating, and this is a feeling of people leaving the nest. And so there was a retreat that was organized, and this was, very small. Idlewild is a mountain village not too far from LA, and in fact, here's one of the trails. I don't, maybe this was a precursor of where we're going to be heading in Telluride, but it was, when you go on a retreat, this is really going out and suddenly you're out far, far from everyone else. And I'm going to play a little clip from a movie that was actually about Misha, but there was a clip in it from this actual event that occurred up in Idlewild to give you a feeling for what the interactions are like, because there was a lot of discussion back then about things like address event, and Misha was central to this. So let's go, and I'm going to find the spot. I've already plotted this out, 48.5. That's where we were.
Now, a year later, Mahowald is about to present an updated version of the communication chip from her thesis to other scientists who, like her, want to build models of the nervous system in silicon. All of the people in this room are working on different aspects of the brain. They're interested in the possibilities of their various projects coming together in a single system. To do that, their chips will have to talk to each other. Misha's communication chip could be key to the project.
You've got people who do work on DC motors and how you control those, the mechanical properties of heads and eyes, okay? And you have to knit all those things together. It's more integrated than, well, we have one student who's working on, you know, vision and another student who's working on color and another student who does something with motor control.
The big problem is how can we have a decentralized project with
Christoph
different
Koch.
people with different aims, some more engineering, some more biology minded. How can we talk to each other so we have a final product which will actually talk to each other?
We can't afford that all of our research is devoted to the machine, because what we're trying to learn about isn't the machine that we're building, it's the brain.
That would sleep so late.
Consideration is an active visual system, one that can act on what it sees. Such a system would have profound military and commercial applications. Weapons could select their targets. Robots could study distant planets. Cars could drive themselves. But that has never been Mahowald's goal.
I'm not really interested in product. I just want to understand what's happening. I hope that people will take what I do and make them products. If they make products out of what I do, it will give life to the work.
Science and engineering often have different goals. An engineer wants to build something that can be used, that can be marketed and sold, and perhaps even a profit made. Whereas a scientist is asking questions about nature, about how do things work. And the ultimate arbiter is experimental science. Whereas for an engineer, the ultimate arbiter is whether it works or whether it's commercially viable.
It's time for Misha to introduce her communication chip. The group expects her ideas to focus on analog technology, and some members are startled when she offers a device that includes digital signals.
I'm just talking about what kind of an infrastructure do you need to be able to do stuff in the analog chip that's worth doing in analog, and what stuff can you push off to something that's off the shelf?
So that means 2 out of every 3 chips are digital.
I'm not stepping that far away from the biology in the sense that I'm still doing analog electronic computation, and all the parts that need to be done quickly are still being done that way.
Well, you're using digital the way it should be used for communications. But what's really nice is that you're going to create an environment that everybody can plug their central chip into. So that's what we all want.
If 2/3 of your board is digital, your team has become a digital design group.
No, it's not true.
No, it's a multidisciplinary team.
I understand.
And I think that we have to do that because we just can't grow those axons.
No matter what you do, okay, no matter what
For
you do,
some, Misha's chip crosses the line. Once again, her work is met with suspicion. The meeting ends with no resolution.
There's a circle you.
So I think it gave you a flavor of the discussion. And from the very beginning, people really went at it, and this analog digital thing is still in the air. But another turning point was in 1993 when Christoph Koch, who was in that little clip, and I were asked by NSF to organize a workshop. And the purpose of the workshop was to create another workshop, another group that would meet. Here are the people who met at NSF in August 1993. This was after, just a few months after that Idlewild group, the retreat, which was in August, in June. So here's the 12 people who were there. What was that? And I've outlined here the people who eventually ended up at the first Telluride workshop. And Avis Cohen is here online. And in addition, Dana Ballard also, who was at that workshop, the initial NSF workshop. Now, what happened was that NSF wanted to start these, these workshops in '95, but we convinced them that they should start the next year. And here's the problem: putting together the workshop that we wanted was, a huge enterprise. And like, where is it going to be? I mean, who's going to come? How are you going to invite people? And what are you going to do with the workshop? And it was an incredible thing. And the first thing we had to settle was where. And we looked at a lot of places. Aspen was very popular, but it was very expensive. Somebody, and I don't know who this is, said that they had gone to Telluride, which was just as beautiful, but a lot cheaper. Just as nice, but half the price. And indeed, that's where we ended up. In fact, we never did we didn't go there to check it out. We just went. We ended up taking trucks from LA and San Diego with all the equipment. And here we are arriving. This is the main street. And here are the people who were at the first workshop. And you will recognize many of them. For example, on the front row, here's Rodney Douglas and Misha. In the back row, Christoph Koch, Dana Ballard, and Toby. And this is actually my IT manager who actually helped set up the IT there and really put in the infrastructure. So it was a group activity, and a lot of the people here are now dispersed through the four corners of the world. Okay, well, here's some basic facts that has emerged. The workshop is actually a 3-week event, and it's really centered on projects. It's been running continuously for 26 years. It's the longest ever funded workshop series at NSF at $100,000 per year, and another $100,000 is actually provided by sponsors. And if you just add up the number of people that have come, it's on the order of 2,000 people. NSF has invested $2.5 million, which I think is really good value, roughly $1,250 per person. We typically have about 100 per year, of which 30 are students who are competitively chosen, and about 70 faculty and assistants. So this is a really focused group. Now, one of the things about the atmosphere is that it's incredibly intense. I mean, people work unbelievably hard, and to give you a feeling for how hard they work, I'm going to show you this little clip. So as you can see, because of the thin atmosphere, it's at 8,750 feet, people work 10 times faster than they do at home. And these are projects that are going on. Everybody's working on their project. Here's an example of a typical daily work schedule. Meet in the morning for a couple of lectures, all very interactive. Afternoon projects, these are major projects I'll be telling you about. And then late afternoon dinner break for sports and relaxation, but then people come back and they work until the wee hours of the morning. In the second week, I bring a group of 10 neuroscientists, and the idea is that most of the people are coming from engineering, but they also need to know a lot about neurons, and so that's what we provide. But we also have, as you'll see, there's also events like the Tequila Party that Toby organizes, which allow people to relax. Now, we saw a pie chart for this Zoom meeting, but in fact, the actual physical meeting, 2/3 of the participants are from the US, and the other third from the rest of the world. It is international. Curiously, Switzerland is overrepresented per population. Somebody could explain that to me someday. Of course, people work hard, but you also play hard. And here, in fact, is Toby showing people he's showing them how to play poker. And on July 4th, the meeting would overlap, and the Neuromorphs would go on in the parade. It's a small town event, and let me play this little clip that I took when I was watching it.
Waves coming out of this brain trust. Some of the most gifted young scientists in America and from around the world attend the Telluride Assembly every summer, and the Neuromorphs never disappoint at the 4th of July parade. I have no idea what's coming on, but I kind of got a sneaking suspicion, as usual, the Neuromorphs are going to take over the show here momentarily.
Okay, well, that gives you a flavor of what it's like, but this will give you a flavor of how beautiful this is. This is the overlooking the valley, the little town at the bottom of the valley. But it's just spectacular, and I really wish I were there. It's just very, very special. So I'm going to give you 3 projects to give you a flavor for what people actually do. And this is one that was put together by 2 engineers and 2 neuroscientists, Ralph and Tony Lewis. were the engineers, and Avis and Mitra were the neuroscientists. And so the idea is to create a walker. Now we know that in the spinal cord, there's a central pattern generator that produces this alternating bipedal motion. And so they put together a circuit that would mimic that. And here is the running man that was built at Telluride. So,
hey, Terry, I think you better play it again because the video is not playing at all for us. It's just frozen. Maybe you can just play it while you talk about it again.
Okay, well, let's see. I've got to go back. Oh, let me see if I can. Well, I'm not sure I can go back. Oh, okay. Can you see this? You can't see it. Okay.
No, there's some problem. It doesn't matter. Just describe it. I mean, basically it runs along, right?
Yeah.
Yeah.
Okay. Sorry about that. Okay, so let me see if I can move forward here. I don't want to get out of it, but I do want to. Okay.
Yeah, Terry, I think you better stop your screen sharing for a second and start it again because there's something frozen about your screen sharing.
Okay, that's what's going on here. Okay, should I try again?
Yeah.
Okay. And let me go back here. Okay, now I will go back to screen sharing. And hopefully we can continue. Yes, okay, here we go. Sorry about that. That was a break. Okay. So now fast forward, that was 2000, no, that was 1999. So 20 years later, there's another group that is at Telluride. And the goal here is to create a powered leg prosthetic. And the person who, the project is really inspired by Rachel Gelhar from Caltech. But here's the project group that they put their heads together and really made this work. And so the idea is you have a powered leg here, which is going to be trained with recurrent neural network to be able to let people walk who don't have a lower leg. And I hope that you can see this. This is now, let's see. There, can you see this? So here's a Telluride test. And as you can see, it takes a little bit of effort.
No, we just see a clock hand. Unfortunately, we just see a clock hand and a black screen.
Okay, well then
there's another video's not coming.
That's okay, but what you saw was that she was walking along and then she fell. But that's okay, because they actually got it to work later. Okay, so here we go again. I'm going to try to get back. Okay, so the other project that I'm going to tell you about is something you're already familiar with, the DVS camera. It puts out pulses on and off, just like on and off ganglion cells. And here's a project at Telluride which used that DVS camera to be able to control a goalie that's going to try to block someone from getting a goal by shooting balls at it, right? And so there's a, you know, it's all run off a laptop, but it's incredibly fast because, of course, there's no frames. It's all event-driven, and it's at the microsecond level. So the question is, can you defeat the goalie? Now, can you people see this?
Yes.
You can see it?
Yep.
So this is a demo of the laser goalie. Right now the laser goalie is sleeping. If I shoot, it'll wake up, and you notice that the laser beam actually tracks the ball as it's coming in. You can shoot quite hard here. And the goalie should still block the ball. Controlling the arm and the 2-axis laser pan tilt, and it turns the laser beam on and off, and it's all powered from USB. Let's see if we can beat it. Before I have.
So Toby was not able to defeat it, nor was I. I don't know if anybody did, but I think that gives us a sense for the fun that you can have in Telluride putting together things. That was a paint stick, by the way, that was holding up the goalie. Okay, well now I've done the once history of Telluride. Now I want to think about the future. And as you can see, it's fuzzy, but welcome to the future, because we are in the future. We are on the Zoom meeting and things have changed. Now, Yogi Berra, the philosopher of the New York Yankees, once said that it's very difficult to make predictions, especially about the future. And I'm going to give you my version of what I think might happen, but of course everybody has their own vision of the future, and I think that's what's exciting, is that there's so many other things going on. And I have to tell you something else, which is that I'm the president of a foundation, the Neural Information Processing System Foundation. It's been running a meeting that has just mushroomed in the last few years. I mean, it goes back to 1987. And last year in Vancouver, there were 14,000 people. And it has lost a lot of the character in the early years, where it was incredibly energetic, incredibly diverse, incredible. And you know, it's a great meeting. It's become the premier meeting for machine learning and especially deep learning. But I think Telluride has actually preserved that early feeling at the early NeurIPS meeting, formerly known as NIPS. And that's what I think is very special, is that the energy, the diversity, the incredible, you know, optimism. Okay, so here is where I think we might be going. And it's inspired by the fact that there's been, as you know, a very big shift in artificial intelligence. Up until recently, the way that you created an AI was you wrote a program. And the cost of programming has gone up because it's labor intensive, but the alternative, which is have a learning algorithm in a network, was very computation intensive, which until recently was really not, you weren't able to scale things up. 2012 was the NIPS meeting where the ImageNet competition shifted. It was a decrease in error by 18% from Jeff Hinton and his students, as opposed to 0.5% a year in computer vision. And basically, as as computing gets cheaper and programming gets more and more expensive, basically everything shifts over to doing it with learning. And this is all chronicled in a book I published in 2018 on the deep learning revolution. But the thing about the book that I want to point out is that what's really going on here is that there's a convergence occurring between AI and neuroscience. Artificial intelligence meets human intelligence. And it's because of the fact that now they can speak the same language. We're talking about units, we're talking about neurons, and there's a tremendous amount of overlap now. It's very exciting. And one of the most inspiring things for me was a paper in 1982 from John Hopfield's group, which was now called the Hopfield Network, which was the attractor states that you could put into a recurrent network, a very nonlinear network. And in fact, the model that has been really put together by people in computational neuroscience for what's called working memory is based on these attractor states. And in fact, for some inputs, you can have two stable states, one where there's a high degree of activity and one where there's a low. And in fact, if you record from neurons in the prefrontal cortex during a delay period task, you see neurons that are, they increase their firing rate when you give them the cue, and then when the cue disappears, you have maintained firing. And so this is what an attractor state can do for you. Earlier in Shishi's talk, she talked about these echo state and liquid state networks. They're recurrent networks, and it's possible to train them. And these are continuous units, by the way. And so you can use things like backprop to actually train it up on a task. Well, here's a very simple task. You give it an input, it's got to integrate the input. If there's no input, you've got to stay at 0. Very simple. Now, there's been a problem, an outstanding problem, which is how can we transfer this continuous network to a spiking network? So I'm going to tell you now how to do it because we figured it out. Okay, so what you do is the simplest thing you can do is just go 1-for-1, 1 unit for in the continuous, rate coded to 1 unit in the spiking, and see how it works. And you can see here, if you just go and transfer the weights 1-for-1, it fails. So the rate network does a very nice integration, but the spiking network fails. But if you decrease the strength of the weight by a factor of 50, it works beautifully. So it turns out it's a very simple solution. You just decrease the strength of the weight, and it's principle. You know why that can happen. So here's the spiking network. So we can now transfer rate-coded networks, created by backprop to a spiking network. So I want to tell you about one little project that we did, which is to compare a recurrent network transferred to a spiking network and compare it to actual recordings from prefrontal cortex. This is a simple task. It's called delayed match to sample. Monkey fixates, a cue comes on, it's either on the left side or the right side, and the monkey has to report whether after a delay, the cue, a sample has come up in the same position or in some other position. If it's in the same position, the monkey moves its eye up, and if it's in the opposite, it moves it down. And so here is a data set that was put online for public, which was from the CRCNS program. And it's great because there are recordings from hundreds of neurons, and here are 150 of them as a function of time during the task. And so we created a network that would also solve this problem, delayed match to sample, and transferred it to the spiking network. We fixed the number of excitatory units to 80% and 20% inhibitory to make it match the architecture of the cortex. And here's the solution to this problem. Cue, sample, if it's the same, you go up, and if it's different, you go down. Now we need a metric to compare. And so the metric is the autocorrelation in the number of spikes that are binned. So here's the decrease in the autocorrelation as a function of time for the experimental data. This tau is what we're measuring here. And so here is the untrained recurrent network, and you can see the recurrent connections had not been trained, so the autocorrelation timescale is very low. Most of them are below 10 milliseconds. Here is a dorsolateral prefrontal cortex. The median of the time lag is 100 milliseconds. And here's the trained network. It also has a roughly 100 millisecond median. And we split them into 2 halves, the long ones and the short ones below or above or below the median. And you can see that the fall off is very similar between the dorsolateral prefrontal in green and the recurrent neural network in pink. So we think we've actually been able to create a tiny version of something that might be happening in the brain, but the difference is that we can actually go in and figure out how this little network will actually solve the problem. And of course, we were expecting that it was going to be an attractor network, right? And especially because these long timescales really were critically important. And as they are in attractor networks, Xiaoxing Wang showed that if you have NMDA receptors with 100 millisecond timescale, you do a lot better in spiking models. Well, we were shocked to discover that it discovered some other completely different way of solving the problem. And it's very satisfying. So first of all, if you look at the the selectivity of the inhibitory interneurons. It turns out that's the secret to this network, inhibitory interneurons, that the positive cue was activated a subset of the inhibitory neurons, and the negative cue was activating the other half. So there are two subpopulations of inhibitory interneurons, and it turns out that it's a flip-flop. In other words, if you look at the connections between the two subpopulations, it's very strong compared to the connections within the population, each of the subpopulations, and the number of connections and their strength. And in fact, if you increase the strength of the between subpopulation interneuron pools, you can actually improve the accuracy of the network, and also the time scale goes up. So this is really telling us something. So here's the new model for working memory. It's basically the excitatory populations that are going to represent during the delay period, the cue, are being, the inhibitory neurons that turn them off are being disinhibited by the winning subpopulation. So it's a disinhibition model. And what's interesting about this particular motif, this architectural motif, is that it has actually been proposed that this would also be a very good network motif for doing decision making, for integrating information coming in from noisy inputs and making a decision. So it's pointing the finger at the inhibitory neurons. Everybody always thought that the excitatory neurons, they're doing the heavy lifting, and it may well be that they are, but the inhibitory neurons may be calling the shots. And there are many inhibitory neurons. Now, there are two predictions that came out of this. Number one prediction was, of course, that they were inhibitory neurons, but there are many types of inhibitory neurons. And so if you look at the what's known about inhibitory neurons, there's one subpopulation, there's somatostatin positive neurons whose density increases from the sensory areas up to the prefrontal cortex, where we know that the working memory circuits are probably dominant. And so our prediction is that there are going to be subpopulations of these somatostatin neurons, which between them form these recurrent winner-take-all networks. The second prediction we made was that by analyzing the firing patterns of the neurons in the network, was that it turns out the trial-to-trial variability in the number of spikes, if you look at any single neuron, for example, was very high. The Fano factor is about 4 or 5, which was really surprising, because in other words, it means sometimes some of these neurons don't fire at all. Sometimes they fire a lot. Very same input. And so we went into the dorsal prefrontal cortex data, and sure enough, it has a very high Fano factor. So I think it means that we're on the right track. And so what we've done, I think, is using learning algorithms is to let the system decide for itself how to solve a problem. And by the way, this mirrors what's gone on in AI. In other words, remember at the beginning, in AI, people had to write a program, which means every little detail had to be put in by hand. And when learning came along, it was possible to do a lot better by letting learning figure out how to do that. Now, the same thing happened in computational neuroscience. All those old models of ours, we basically put them together by hand. We put the constraints in from neuroscience, but at the end, there are thousands of parameters that had to be fixed. We twiddled with them until we finally got something that worked. It wasn't always robust. And in fact, I always think of it as being lost in parameter space because of the fact that, who knows how many different architectures there might be, or set of parameters. And this is something that Eve Marder, the point she made, is that there are many networks that could solve the same problem. So another signal event that is going to be very important for the future is the fact that 7 years ago, then President Barack Obama launched the BRAIN Initiative. And since then, it's been spectacularly successful in developing innovative neurotechnologies. And it's brought together engineers who like to build things with neuroscientists who need things to be able to record from more neurons, to be able to reconstruct the connectomic diagram of the connections, and of ways of manipulating neurons, optogenetics, and it just mushroomed. And so now we have much more data than we ever had before. And now we're going to actually have the ability to actually go in and test ideas at the same time that great progress is being made in artificial intelligence. And here is where I think the two are going to come together with neuromorphic engineering. Why? Because it's the neuromorphs that have preserved the idea of spiking as an important feature of computing, low energy computing. And the fact that we can now take these deep learning networks and convert them to spiking networks means we can download them into chips. And I think this is really exciting. Basically, it's the same principle that I predict will go on over the next 10 years as we can now take advantage of this learning curve and be able to now take the fantastic engineered chips that you heard from Shishi and actually download solutions to difficult problems and put them into edge devices. I just want to mention that the project I told you about, it's on bioRxiv. Robert Kim is a grad student finished up recently who did a terrific job. And just to give you a teaser, we have a paper under review in which Robert has figured out how to actually do the learning on the spiking network itself. You don't need, and there's a lot of people who have come up with algorithms, but his seems to be particularly effective. And I think that this again it's another step forward. Okay, well, end of story. I really am pleased that I had this opportunity to give you a feeling for what it's like to be at Telluride. Of course, this unless you're actually there, you don't know what it's like, but it's really exciting, and I'm really looking forward to the next 5 years that Cornelia has made possible for us. And thank you.
Great, thank you, Terry. Echo your comments about how deep we felt this loss of our Telluride community was felt for a lot of us this summer. I know I heard from a lot of our organizers, falling into a sense of depression over the loss of all of our best friends. So it's great to have that perspective on the last several decades of excellence that you helped enable for us at Telluride. I know that Toby has been collecting questions. Toby, do you want to unmute and read anything that we want to ask Terry before we move on? Toby, you there?
Yeah.
There we go. Cool.
You can all look at the questions here. I mean, the number one question, the number one voted question from Sean is what are some of the top unanswered questions or critical challenges in the field at the moment? Maybe Terry, you could give your top 3, and then Chi-Chi or anybody else could chime up with their top 1 question. What's the top unanswered question in the field of AI? Terry.
Okay, I'll give it a shot. How does the brain work? I'm all in with Misha there. If we could figure that out, then we would have a fantastic neuromorphic, field day, actually building these things. And actually Feynman was the person who said that you don't really understand something unless you can build it and it works. And so I think that's what's going to happen.
Okay. I guess we better move on though, unfortunately. I hope we can come back to some of these questions later on during the other discussions. Maybe we should close the door here. I think we have to move on with the program now, unfortunately. There are the other question. You maybe can answer this very specific question, Terry. In the disinhibition model of working memory, do they observe gamma or any other oscillations related with higher cognitive functions? This is something you've talked about a lot, right? Especially when you talk about your sleep research.
Yeah, well, the background here is that no matter where you look in the brain, there's oscillations. That's different frequency bands and different location and state dependent. So the answer is we do see oscillations, but we haven't explored them yet. The gamma band is 30 to 80 hertz, and it's known to be important for alertness and attention. And so my guess is that as we scale things up, that is going to be more and more important. By the way, we do know that it's not the somatostatin neurons that create the oscillations. It's the parvalbumin PV basket cells that have a dense inhibitory projection to the soma of the neuron. The somatostatin cells project to the dendrites. So we think that there's actually two systems. One that's responsible for the oscillations, and the other one is responsible for the flip-flop. And what are the oscillations there for? We have a paper coming out in Nature that will be out soon. It was recordings from monkey cortex during a task in which the monkey had to detect very weak stimuli. And we showed that the phase of the traveling wave, it's not an oscillation, it's a traveling wave through the cortex, allow you to predict with explain 50% of the variance of whether the monkey is going to see it or not. So it's a direct connection to perception. So I think that these oscillations are there for computational reasons.
It's unclear whether AI can exploit that in some way, given the current approaches. But I guess we'll find out. Guido, I think we should move on, right?
Yeah, that sounds good. And conveniently, I believe you're hosting our next section. So thank you, Terry, very much. That was fantastic. We're getting a lot of good questions in the Slack. And so we'll gather anything together that makes sense to send it over. And we'll make sure that all of the videos that you played get shared back to everyone else as well. With that,
by the way, go ahead.
Go for it, Toby.
Yeah, by the way, we're attempting to use a Slido thing that's also used